Hello, let us get started with this shorter lecture than usual, I hope. Sorry, the class has been canceled and I have to record this now. It's always a little awkward talking to myself, but let's just start from where we left off last time. So we ended on essentially this iClicker question, and I am going to give it again in today's slides. So we'll just breeze on past this for now. But the idea was the priority queue was sorting things in a weird way, and we want to prioritize it in a different way. Okay, so that is the slides from last time. I'm going to go over that again on today's slides. And this is really the last set of slides that I have like pre-made for us. And I will talk about the schedule in just a second. So this is like a wrap-up, and let's go straight into a similar question from last class. So again, we're trying to give a priority queue based on pointers, and if we had class today, I would have given this all over again. But we have some different things inside this array, and the idea is take a minute, pause the video if you can, try and figure out what the answer should be, and assuming you're back now, let me show you why it's going to be 92, then 5, then 20. So the answer should be B. And so the real hardcore reason, as we got into last time, is this right here. So our array, ARR, in memory, had these three elements, and let's see, 25 and 92. And the addresses of this array, because that's what pointers are, they're just addresses. The addresses of all these elements in this array are maybe 100, 104, 108. It doesn't really matter what they are, but they're going to be in order. So they're going to have different addresses in actual memory. Whenever we load this program a different time, it'll get loaded into a different place in memory. But the addresses of this array will always be ascending. Addresses of larger indices are always greater, no matter where we put this array in memory. And so it's going to prioritize based on these pointers, 108, 104, and 100. And the default priority queue, the default heap in C++'s terminology, is going to sort these pointers now, because that's what we're pushing. We're pushing pointers. It's going to sort them by the biggest thing first, because the default priority queue is a max heap. Okay, so we're going to get the element that is the max address, then the next one, then the next one, 92, 520, in that order. So I hope it makes sense why it's B, but maybe we don't like that. So the idea is we want to change how this priority queue prioritizes pointers. And using pointers is kind of useful, though. Maybe you just want to never use pointers again and that will solve the problem, but that is not the real answer here. We're going to find a way to do it in a different way. So pushing pointers to a data structure is actually quite useful. Pretend that your data structure, the elements inside, held some large type. That you want to store are some large type in terms of memory. Say each element is like a megabyte or something. You don't want to copy them over, and that's what would usually happen. So you'll end up using pointers instead, and that is going to save you a lot of space, because you don't have to copy a whole megabyte. You just have to copy a 4 byte, 8 byte address, depending on whether you're using a 32-bit or a 64-bit machine. So that's very useful. And so sometimes we do want to add just pointers, but we want it to be sorted by the actual elements inside. So we want to get back maybe 2, 10, 80, or 80-10-2 instead of 82-10. Okay? All right. So the way that we got around this problem is to change how the default priority queue prioritizes its elements. And by default, it's making a max heap, and it's going to compare things for higher priority using the less than operator. So it's going to check, hey, is this element B, does it have higher priority than element A? Maybe it needs to move it up in the tree. If so, it's going to check, is B greater than A? It's going to do it in that order using the less than operation. You can think of the less than operation as actually a function call, right? You can think of it all out in front just like that, a prefix notation, and so on. You can convert that to a less than function, and really it's just some function that priority queue sees called compare, no matter what it's called. So it's going to compare B to A, but A comes first, and if this returns true, it's going to mean that B has higher priority than A. So if you're going to make your own comparison class and give it to a priority queue, you have to think about it in this way. When you make your comparator object, your class that compares things, your functor, you can think of it as always being given A and B in this order, and as long as it and whenever it returns true, it's going to mean that B has higher priority than A. So, like we did before, if you want to make a min heap, you would give as your compare function the greater than operation, okay? Because it would compare using that, so if A compared with B is true, then that means B has higher priority. If you use the greater than operator, that means that A, I don't know if I can write this, is greater than B, which means that B is less than A, okay? It's just the order that kind of trips people up, and hopefully that makes a bit of sense now. But we're not comparing just actual values anymore. We're trying to compare pointers, okay? So let us make a comparison class called CMP pointer and give it just that. And have it so that it prints the array in sorted order from smallest to biggest, let's say. So we want to get out from this 2, then 10, then 80, all right? And so we're going to have the priority queue prioritize these addresses in a very different way, probably by following those pointers, all right? So let me make a folder for today. No, this is the completely wrong terminal. There we go. What do we got? Today is the 26th. So I'll make a file called compare pointers.cpp, and let's go ahead and open that. And I'm going to use a lot of what we did last time, so hopefully I can include a lot of this, and then I'll close that. Okay. Compare. Oh, I made this file in the outer directory. Let's fix that. I didn't change directors into. Move compare pointers.cpp into today's folder. There we go. Now, let's paste up most of this, and let's make our own again, and we're going to make an array. We can do it in any order. Let's actually do it 10 to 80. Let's just do it in like reverse order maybe. 10, 9, 8, 7, 6, 5, something like that. So what we want to do is make a priority queue with pointers, of course, and then have it sort them in a different way, have it prioritize them in a different way. Let's see here. Okay, that looks a bit better. So we need to make this CMP pointer still. So we're pushing each address of each array element. And while the priority queue is not empty, we're going to get the thing on the top and then pop it. Okay, so there's that. So now we need to work on making this CMP PTR comparison class. Class, CMP, PTR. So what it's going to do is it's going to have that overloaded function call operator. So bool operator function call. And it's going to take two things. In this case, they're going to be int stars, okay? Pointers to ints, because that's what we're going to give to this priority queue and have it compare for some sort of priority. So int star A, int star B, we'll give it. We don't actually want to compare these things, so we'll make them const pointers. We don't want to edit these things, so we'll make them const pointers. And let's see, we'll return whether or not, so we want to have B be of higher priority than A if it is smaller than A. So we're going to do something like A greater than B, but we're actually going to compare the actual values inside. So we want to compare the values that the pointers store, not the addresses themselves. Okay? So then we're going to say star A greater than star B. So now this B, this pointer B, has higher priority if by following it, and by following the pointer stored at A, we see that the values there are smaller. So star B, B has higher priority than A if this returns true. So now what's going to happen is when it's going to make this queue, it's going to compare each element to see which one needs to go up top as the root, and it's going to see that 5 does, because even though the address of 5, the element 5, has the highest value as a pointer, it has the lowest value as an actual value. After you follow that pointer, let's say. Okay. And thanks to our comparison class, that'll put it at the very top. So let's compile and run this and watch it work. So make compare pointers. Oh. All right, what have I done? Oh no. Let's see here. Error is a private, oh, excuse me, I forgot to say public here. There we go. Gotta make that a public function so you can use it from anywhere. Compare pointers. We see 8, 9, 10. Oh, oops, because I only pushed the first 3 elements of this array. Let's push all of them. So there's 1, 2, 3, 4, 5, 6 now in my example. But it was comparing those first 3 correctly. Oops, did it not save in time? There we go. 5, 6, 7, 8, 9, 10. And so 5 has the highest priority now because we're following those pointers. Okay, hopefully that makes some sense. Let us go back to the slides. And now I'm just going to talk about a bunch of logistical things. So let's talk about some questions from midterm 2. The first was my mistake. I should have said something like n squared here. No, sorry, n squared here instead of n. I shouldn't have given you both O of n and O of h as options. So what we've done for binary search trees, we talked about the worst case running times for binary search trees in class in terms of this variable called h. And that was for demonstrative purposes to make it easier. That's what I was hoping that you would pick on the midterm, but a lot of you probably went, when you studied, to a place like Wikipedia, so binary search trees. And you probably noticed that, oh my goodness, in the worst case, they're saying O of n everywhere. So, why is that? And I hinted about this in a previous class, but the worst case is h, but it also is n at the same time. In the worst case, though, h is equal to n. For the very reason that a number of you picked that answer. If you have a binary search tree, and you give it all of the keys, maybe in sorted order or reverse sorted order, you'll end up with a linked list. And so height equals 3 or 4, depending on how you define it. And that means that O of h is equal to O of n in that case. So in the real world, now that we know this, in most textbooks and future algorithm classes, you'll see the worst case for binary search tree operations given in terms of n, and the worst case really is O of n, because the height of the tree could in fact be the number of nodes. Okay? So I think for the rest of this class, now that you know this secret, instead of O of h. And so what I should have done on the midterm was not give you both those options, because that was a bit confusing. I'm sorry about that. The other thing that I want to talk about from the midterm is the question F, so the best case minimum for linked lists. A number of us picked constant time, and that's incorrect for a general purpose list. And let's talk about why. Let's see here. So pretend we have a linked list. And we don't know about its order. So we could be given it in any order, 2. A minimum function on a potentially, like a generic linked list that we know nothing about, a minimum finding function, let's say, has to iterate through the entire list. So what that means is you can never stop early, because the algorithm is you can never stop early, even if you're given a sorted list. Because that would be an incorrect implementation. So correct implementation of the minimum function looks something like this. Iterate through the list, or let's say pick the first element as the minimum, and then iterate through the rest of the list and update the minimum value as necessary. And then finally return the minimum. So look at where we return. It's always at the very end. After this loop, which is going to be O of n work. Always at the end. We can never return early, because we can't return early. The best case is equal to the worst case, which is O of n time, if we know nothing about the linked list. Okay? Even if you were given a sorted linked list, you would have to run the same minimum function that would work for any of them. Okay? So I hope that makes sense why the answer is not O of 1 for that question. Okay, oh, don't want to go to that. So that's that, and that's some midterm 2 stuff I wanted to talk about. And now let's switch gears to your programming assignment, because that's going to be due. And let's see, do I want to go to the calendar now? Maybe I'll do it in just a second when we talk about the final. So in your program assignment, you're going to try and figure out the running time of some of your functions. And one thing that you can use is this ctime header. You can also use the chrono header if you want to get fancy and use real C++ stuff. But I think it's a bit easier to understand the ctime functions. There they are right there. Now, inside of this, we have a few types and a function called clock. And clock will return something like how long it took to do something. It'll return some value at the very beginning, and then if you call it again later, the clock will have ticked. And you can subtract those things and see how long it took. Okay, so this is a C example. Let's do this in C++. What do I want to call this? ctime example maybe, or timing example. So I'll make a file called timing example.cpp, and you'll need this for your programming assignment too, when you're making your fancy graphs. So timing example. Let us include ctime, include iostream, use namespace std, and let's have a main function. And let's do something that takes a long 10 times that amount. There we go. There we go. That took some time. And so the idea is we want to take this clock type and see how long, just how long it took. So if we go back to the documentation here, we see that we can subtract these two clock types. So this clock function returns a type called clock t, which will be included when we include the file. So let's do just that. So let's make clock t. So time now, time before equals, we'll call the clock function. And then we'll do clock t time after equals clock again. So time will have passed. So clock returns something else. And so if we print that out, this took blank and that's called clocks. It's some random type that it's made for itself that doesn't really have any easy definition. So the compiler is able to choose any unit that it wants for this, but we can always divide by this constant here called clocks per second, which is also a part of this library. Clocks per second, and that'll give us the number of clocks per second, and then we can output seconds, which is a bit closer to what we wanted. That is, no, oops, we want to subtract. Minus time before seconds, and to get that we're going to divide by clocks per second. But these are both going to be integer things, so we have to make one of them a double. So static cast double clocks per second, and that'll give us seconds. Okay, and so it looks like clocks are like almost a microsecond exactly. But if we wanted that in something else, we could say, I don't know, times 1,000 for milliseconds, or times 1,000,000 for microseconds. Okay, so now we can see that this is useful, and it'll tell you how long something took, as long as you remember to actually subtract those things. Okay, so that is measuring times. And then let's talk about some other logistical things like the final. So let's go to the calendar. So we are, refresh, we are here, and the final is in just a little bit over 2 weeks. First of all, before we talk about the final, the last due date for anything is the 5th of December, and you can't turn anything in late after that. So let me just write that down. December 5th is the last day to turn in anything. So keep that in mind when you're working on your program assignment and that extra credit lab. Now, so we're going to do the final. And same as before, you get to bring notes and things. Here are some sample exams that I've gotten from previous years of this class. And here are all the topics that you need to look into. I'll try and give a good chunk of things, a good chunk of questions on things that we covered after midterm 2, which are like stacks, queues, and heaps. But really, I'm going to give all of these things. So definitely running time analysis. That is huge and very important. So please go over that. And then we talked about templates a bit. So look into that. And we've also hit a few of these STL classes. So know how to use them. If you're given like a documentation page or just code with them being used, you should know what they do and how to make them do what you want. Let's see, anything else? Yeah, you're still going to have things about binary search trees, which is very important things to know. Talk about recursive implementations on binary search trees. We haven't done a ton of them, and I'll give another example next class. Okay, so study all those things. It's going to be essentially cumulative because there's no real getting around that in this class. So that brings us to these last 2 lectures, because this is today and there's no class on Thanksgiving. I hope you guys have a good break. But these 2 classes are going to be mostly review if we don't do anything else. So yeah, the final 2 classes will be essentially review. The first on the 3rd, so on 12/3, I will bring some material that I make for myself, and we'll just walk into that. It'll be the end of these slides, so I'll save those for then. I'll bring in some review material. On 12/5, I will finish anything I didn't, but I'll mostly open the floor for questions from you guys. So bring questions on 12/5, please. Okay. And so yes, it's going to be review. I don't think I'm going to have any iClicker questions, so you don't have to show up. But if you want to, I'll be reviewing the final week of class. Okay. That is all logistical things aside. Oops, I want to go back here to the slides now. So I just want to give a few final examples. Here are queues. We talked about those before. They're different than priority queues or heaps. A queue is just something that is like a line of people. It's got a front and a rear, and you take from the front and you add to the end or the rear, okay? And so we've talked about this before. You've got all these operations that look like stack operations, but they're not quite. And so when you push, you add to the beginning, or you add to the end, and when you pop, you add to the, you take off the beginning. So queues, remember, push to the end, pop from the front. that's very useful. And let's see in these last couple slides. Yeah, let's talk about using queues. So let us pretend for some reason that we were in a universe that didn't have the queue class. Let's implement a class that is a queue, but let's do it using two stacks. So I encourage you to like pause the video right now and think about what this would entail. It's kind of interesting. But think about how you might implement this class yourself. So queues using stacks. So it's definitely doable. Oops, I can't draw a straight line. It's definitely doable, so let's think about this. So let's pretend I have two stacks, S1 and S2. And I want to simulate a queue. Like if I add 1, 2, 3, 4, I will pop them off in order. 1, then 2, pop, pop, etc. 2, then 3, then 4. But if I add them to just one stack, 1, 2, 3, 4, I'll pop them off in reverse order, 4, 3, 2, 1. And I hope you notice the naive example, or the... All right, so the naive solution would look something like this. For push, we're going to want to add something. We're going to pop everything from S1 into S2. Then push the new value into S1. Then pop everything back from S2 into S1. All right, so that would look like this if we wanted to add 1, 2, 3, 4. So we'd have S1 and then S2. So the first time we want to add 1. So we're going to pop everything from S1 into S2, push the new value. There's nothing there. We'll push our new value 1, and then pop everything back from S2 into S1. There was nothing there, so we'll do nothing. All right, now is where it gets interesting. So when I added a 2, I'm going to pop everything from S1 into S2 in order, add my 2, and then pop everything back from S2 into S1. It looks like that. Oh goodness, does S1 look like a queue now in the correct order? Now if I wanted to push my 3, I would pop everything off of S1 in order. That means the 1 goes first, then the 2, right? So I'm going to end up doing this. 1, 2. Then I'll add my 3. And then I'll pop everything back. So 2 first, then 1. Okay, you can see how this is working. And I think you can convince yourself that you're going to end up with 1, 2, 3, 4 if you push them all in this way. And so now pop is super easy. Pop from S1. And then top is very similar. Top is just look at the top of S1. And so this would be O of 1. This would be O of 1. But this pop everything over and back again, that's essentially taking O of n time, yeah? Or n are the number of elements in the stack. Both stacks, so the queue. So that's a naive solution. There is a better way to do this, though. Fancy solution. It works something like this. So let's see here. For push, we are just going to do one thing. Push to S1. Okay? For pop is when it gets a little weird. We're going to if S2 isn't empty, pop everything from S1 onto S2, and then pop S2. And then top can be, is very similar to that, where you just replace pop with get the top of. Top is essentially that, except for right here, you get the top. Get the top instead. And this is a bit interesting. It's going to work. Let me show you pushing 1, 2, 3, 4. Here's S1 and S2. So let me actually do it in a weird order. Let's push 1. These are queue operations that I want to do, that we're simulating with stacks. I'll push 1, push 2, pop, push 3, pop, push 4, pop. I need to pop 1, 2, 3, 4 times for fun. Okay, so here's what's going to happen. That's a P for push. Okay, when I push 1, remember what happens. I'm just going to put it right on S1. When I push 2, I'm going to put it right on S1. So it's going to take O of, oh, that's a weird looking O. There we go. It's going to take O of 1. Now, once I want to pop, I'm going to do this. I'm going to say, well, if S2 isn't, oh, sorry, if S2 is empty, and then pop S2. If it's not empty, just pop it. Okay. So the first time S2 is empty, and we're going to pop everything from S1 onto S2. So it's going to be 2, then 1, and this is now empty. And then we're going to pop from S2. So we're going to get our 1 out. And oh my, this is working. This seems to be working right. Now we'll push 3, which just involves putting it on S1. And then we're going to pop again, but S2 is not empty. So we'll just pop it. We'll get our 2 off. Right? Just like that. So we're good. Now we're going to push 4, just like that. And now we're going to pop. Well, S2 is empty, so we're going to move everything over. So we're going to pop 4, push it on S2, pop 3, push it on S2, and then we'll finally pop S3, or pop S2, and get our 3. And then once we pop it again, we'll get our 4. And so sometimes we don't have to move anything around for a pop. So sometimes it's O of n, sometimes it's constant time. Let's see if I can move that over there. There we go. And that's the same for top. What happens though is this is going to average out. This is fancier math than we know about in this class, but this averages out to, believe it or not, constant time. That is a 1. And this is kind of weird and hard to believe. It's the topic of an algorithms class, but this is the same reason. So the proof is beyond the scope of this class, but it's the same reason though, that dynamic arrays, like vectors, for example, have a constant time pushback function even though they sometimes need to resize the array and copy everything over. That's a very long little blurb there. Let's see if I can make that a bit bigger. There we go. So this, in the average, in the end, this becomes constant time. And so this is a fancier way to do this. So I'm not going to test you on how to make this fancy solution, but I hope that you could come up with maybe the simpler solution in a test example. Okay? And then the final slide for today is just about noticing problems and how to solve them with data structures, because now we know about a bunch of data structures. We need to use them in the wild on cool things. So here's a function. Oops. Here's a function. It does some mysterious thing. Let's actually understand what it does first. So we're going to give it a vector and the size of that vector, which you don't really need. We're just using it so that we can talk about the size of things. So you could always do a.size, but we're going to say the size of this vector is n, and n times we're going to do something. Okay, so these things right here, those take constant time. This loop, we need to figure out what it does and how long it takes. And this stuff right here is going to be constant time. And this is a loop, so it's going to be n times whatever this is. So let's think about this. This is going to, right here, iterate from I plus 1 to n, which means it's going to iterate n minus I plus 1 times. Okay? And so it's going to go from n minus 1, because I will start out being 0, to n minus 2, all the way down to 1, all the way down to 0. So what's going to happen here is this is going to be some constant amount of work, some constant c. This is some constant work inside. This will all average away to become some kind of constant. This is O of 1 stuff inside of that inner loop. There's the outer loop. So number of steps will look something. So the number of steps total is going to be something like some constant times 1 plus, just get rid of the 0, 1 plus 2 plus up to n minus 1 times. And if you guys remember, this kind of sum, it'll end up being this, c times n times n minus 1 over 2, which is O of n squared. So this algorithm is going to do n squared work. And what is it doing, though? It keeps on finding a minimum and setting that to be the ith element of the array. So this function keeps finding a minimum and sets it to be the ith element of the array. It moves it there. So for example, if we had the array 3, 2, 1, when I is 0, it's going to look from all of these and find the minimum. It'll find the 1, and then it'll swap it there. So when I is 0, I is there. It'll find the 1 and put it where it needs to go, according to what it's doing. 2, 3. And then when it's here, it'll find the minimum. It'll find that it's itself. It won't do anything. And then here, when it's here, it'll find the minimum. There's nowhere else to look. And it'll put it there. So it's sorting the array. Sorts the array. And it's doing it in O of n squared time. But we could do a bit better, because you see how it's always finding a minimum? the smaller minimum. This, by the way, is called selection sort. It's a valid way of sorting, but we can do a bit faster, because what is something that allows us to easily get at the minimum element? We can put all these numbers into a heap, a min heap. Let me type this. Then finding the minimum would only take log of n time. We'd do that n times and end up with a O of n times log of n algorithm, which is asymptotically faster than selection sort, what's above. So just noticing, and that's the key for after you get out of this class for the final, it's important to notice what is happening in your program and see if there are any data structures that you know about, because now you know about a lot. Oops, data structures. See if there are any data structures that allow you to complete the same task more efficiently. Okay, so that is essentially deep down the purpose of CS24. We're trying to teach you how to look at all these data structures that we learned about and use them in a way that makes the algorithms that you will write from now on more efficient. Okay? So with that, that is all I'm going to talk about today. I will see you after Thanksgiving. And then we're going to complete, during the first part of the review, this slide into this one. So you can cheat and look ahead, that's okay. We're going to fill in this table, and I'm going to talk about each and every one of these algorithms in unfortunate detail, enough that we can understand for the test why all of these running times are the way they are, and how to be able to combine them and implement them on a test. I want to get that all in your heads, and so that is where we will pick up next time. So I will see you then.